Good morning. Today we can start with measure integration. Last few classes we are already discussed about the Lebegue integration. In that last two classes we discussed about the Lebegue integral of a bounded function over a set of finite measure. And related theorems with a simple function. In the last class, we discussed about one of the important theorems related to Lebegue integral, that is bounded convergence theorem. That bounded convergence theorem is a little bit third principle concept. And also some of in the definition of integral of a non-negative function, measurable function, also we discussed in the last class. Today's class, I might focus mainly on the integral of a non-negative function. In that non-negative function, we already deduced one of the theorems, that is integral upon f plus g over e is less than or equal to integral upon f over e plus integral upon g over e, where f and g are non-negative measurable function. That theorem we already discussed. Here today we will discuss about the Fatous lemma. Fatous, sometimes we are telling Fatous, you become silent. Then after that we will discuss about the monotone convergence theorem. Then integrable over measurable set we will discuss today's class. The general Lebegue integral also we will sketch it on in the end of this class. Now, today's class, we start with Fatous lemma. Here, what is the Fatous lemma states? Here, there are sequence of non-negative functions are there. Means here, like if fn is a sequence of non-negative measurable function, and also if limit n tending to infinity, fnx is tending to f of x almost everywhere on the entire E, then integral upon f over E is less than or equal to limit, that is inferior limit of n tending to infinity, integral upon fn over E. This is the Fatous lemma statement. If fn be a sequence of non-negative measurable function, limit of n tending to infinity, fnx is equal to f of x almost everywhere on E, then integral upon f over E is less than or equal to limit of n, that is inferior limit of fn over E. Some of the textbook, they are written that limit of n tending to infinity fnx. Instead of fnx, here infimum of fnx is equal to f of x almost everywhere will be there. Both are one and the same. Don't worry about that one. Here, how to prove this? First, we can start without lots of generality. We assume that convergence is everywhere. Means if it is already converges to fnx, limit n tending to infinity, fnx is equal to f of x, means it is converges in everywhere. Since the integral over a set of measure is 0, suppose any one of the portion that is equal to 0, the measure is equal to 0, means that is also 0. Then whenever we are dealing with the measurable function with respect to integration, means first we can take a bounded measurable function because it is already a non-negative measurable function, means you know the definition. There is a sum h is a bounded measurable function which is less than or equal to f. That is the definition. You already aware of the definition. This one, the definition, you already known this. Using that definition here, we can use that and also vanishes outside the set of E dash of finite measure. Here in this context, we are defined or setting a sum h and x. It is in terms of related with this h and f, means h and x, h of x into f and x. In this, we are defining h and x by setting a minimum of this, because here inferior limit is there. That's why we are choosing minimum of set of all h of x comma f and x. Here h and x is bounded by the bound of for h, and also it is vanishes outside E dash. Also, because h and x is we are choosing h and x, it is related to f and x. F and x is a sequence of bounded functions will be there, that measurable function. In that, we are choosing h and here h is related to that, and h and x is related to h and x is also tends to h of x for each x belongs to E dash, because it is vanishes outside. We already know the bounded convergence theorem. What is the bounded convergence theorem tells? Here, the bounded convergence, it is bounded to the particular value hn become fn, then that is integral upon. You already know this theorem. Here, let fn be a sequence of measurable function defined on a set E of finite measure, then finite measure. Suppose that there is a real number m such that it is bounded. Mod fn x is less than or equal to m. M is any real number for all n and as well as x. If f of x is equal to limit of n tending to infinity fn x for each x in E, then definitely integral upon f over E is equal to limit of n tending to infinity integral upon fn over E. This is the bounded convergence theorem. Here, in proving Fatous theorem lemma, here we are applying here because hn is a boundedness is there, also converges to hx, then integral upon h over E is less than or equal to integral upon h over E dash. Then definitely this is equal to limit of, because limit of n tending to infinity h and x is equal to hx. Outside the limit, x belongs to E dash. Then definitely it is limit of hn over E dash is less than or equal, because it is bounded to the f and x. Then limit of n, that is limit inferior, is equal to integral upon E over fn. Here this is inferior limit is there, then we can apply here superior over all the bounded measurable function h is less than or equal to f. Means if you are applying this, this become integral upon f over E. This is less than or equal to limit inferior of limit of fn over E. This is the Fatous lemma. You must remember this. Next, one more important theorem, that is monotone convergence theorem. Here, the part of the major part of the proof is Fatous lemma. First, you can prove the Fatous lemma, then only you can prove the monotone convergence theorem. Here, what is the statement of monotone convergence? Here, let fn be a monotonicity, means you know that increasing sequence or decreasing sequences will be there. Here, let fn be a increasing sequence of non-negative measurable function, and also let f is equal to limit of fn n tends to infinity, then integral upon f is equal to limit of fn. Means the part of the proof we already proved by Fatous lemma, means here fn is a increasing sequence of non-negative measurable function, and also let f is equal to limit of fn, then integral upon f is equal to limit n tending to infinity integral upon fn. Suppose we are not mentioned here n tending to infinity, it is understood that yeah, it n tends to infinity only. Here, the first part of the proof is Fatous lemma. First, you can prove that theorem. Then you can prove the other part, greater than part means first, but for each n, fn is less than or equal to f. Apply here integral fn is less than or equal to integral upon f. Then if you take a limit superior of this, then definitely limit of integral upon fn less than or equal to integral upon f. Then and also integral upon f over e is less than or equal to limit inferior of fn is less than or equal to limit superior of fn in general sense, but this is less than or equal to integral upon f over e. Then this is less than and as well as greater than means definitely this must be equal. Means integral upon f over e is equal to limit integral upon fn over e. This is the monotone convergence theorem. Suppose in the examination state and prove monotone convergence theorem means first you can state the monotone convergence theorem, then first you can prove the Fatous lemma, then only you can sketch it out the monotone convergence theorem. Is it any doubt?
No, sir. No doubt.
No, sir.
Okay. Next is related to this monotone convergence and theorem and non-negative measurable function. This is the corollary, it is deduced. Let un be the sequence of non-negative measurable function and let f is equal to summation of un. This is sum of un. It is already non-negative measurable function. You must remember, if it is a measurable function means it is already satisfies the conditions of measurable function, as well as that measurable function is related to set concept. That is also, there is a some set that is already a measurable set. These concepts are one and the same. That's why we derived first measurable set, then measurable function. Now we come across integration. Whatever the theorems we deduced in the measurable set as well as measurable function, that all are holds good here. Here first we can set let Sn is equal to this integral upon I running from 1 to n ui. Since ui are non-negative, and also here it is a monotonicity is also happened, Sn is less than or equal to Sn plus 1, because Sn is an increasing sequence of non-negative measurable function. And also here you get, if a limit of n tending to infinity, Sn is equal to f. Hence, by the monotone convergence theorem, we have integral upon f over e is equal to limit of n tending to infinity, integral upon Sn. This is same as Sn is, that is in terms of ui's, that is summation I running from 1 to n ui. You know that sum and integrations are one and the same, but respect to the particular stage, we can interchange these two. Then this become limit n tending to infinity, summation I running from 1 to n integral upon ui. Then you get a proof for that one. It is same. Because limit, if you apply, that is generalized version, then that is summation I running from 1 to n integral upon ui. Now, one more corollary related to that. Let f be a non-negative measurable function and ei's are disjoint sequence of measurable set. And that measurable set can written as E. E is equal to union of EI's, I running from 1 to infinity. Then integral upon F over E is equal to summation I running from 1 to infinity integral upon F over EI. Means here what is given, F is a non-negative measurable function, then definitely there is some bounded measurable function will be there in the non-negative side. Means you know that chi of E means that is characteristic function is a bounded function, then definitely here we can choose the characteristic function. Means here let F is equal to F times chi of E, means it is a bounded to a bounded measurable set, and also here EI's are the disjoint measurable set. Disjoint measurable set means E1 intersection E2 is equal to 0, E2 intersection E, that is 0. Then in a measurability, you know that countable additivity property also. Some become measure of EI. Is it correct? Here, F is equal to chi E we are taken, then integral upon F over E is equal to integral upon F into chi of E. F into chi of E means it is F into measure of E, because integral upon chi is measure of E, then this can be written as F into summation I running from 1 to infinity measure of EI by the countable additivity of M. Then summation I running from 1 to infinity F can be taken inside by using previous corollary. Then sum and integrations are one and the same. The measure of E, and that is same as summation I running from 1 to infinity integral upon F over EI. Measure of E can be written as integral upon F over EI. These are the some of the corollaries we are deduced from the bounded monotone convergence theorem. Now one more definition related to integrable. When a non-negative measurable function F is said to be integrable over a particular measure of set E, if it is integral upon F over E is finite. Finite means less than infinity. Now we will using this, we will prove some more concept related to non-negative function become an integrable over E. This is exactly similar. Proof structures are similar to previous theorems, but you must aware of this. Let F and G are two non-negative measurable function. If F is integrable over E, here F is integrable, one is given, one of them is integrable over E, and there is a monotonicity or there is a condition is given G of X is less than F of X on E. Then G is also integrable on E, and integral upon F minus G over E is equal to integral upon F over E minus integral upon G over E. Here F and G are two non-negative measurable function is given. F is integrable over E, then F of X is greater than the G of X in the particular E in the measurable set. Then definitely this G is also integrable on E. Then if these are the conditions we are given, then integral upon F minus G over E is equal to integral upon F over E minus integral upon G over E. Here G is smaller, then we can F can be represented in terms of F and G, that is F minus G plus G, means adding and subtracting G here, we can represent this one. By using theorem, integral upon F plus G can be split as integral upon F over E plus integral upon G over E. That theorem you already know. Using that concept, integral upon F over E can be written as integral upon F minus G over E plus integral upon G minus E, because it is same F minus G of X on E is positive. Then you know that this is left hand side is given that it is integrable, means it is finite. Therefore, definitely this is right hand terms are also integrable. Both are, hence it is finite. Left hand side is finite, means right hand side is also finite. Means this is positive, then definitely D is also integrable. This gives that integral upon F minus G over E can be represented as integral upon F over E minus integral upon G over E. Is it any doubt?
No, sir.
Now we move on to one more theorem. Let F be a non-negative function which is integrable over a set E. Then given epsilon positive, there is some delta positive such that for every A, means there is a some A will be there. It is subset of E with measure of A is less than delta. You know that here F is a non-negative measurable function is there here in E. In this, there is some epsilon positive and also there is some delta is also present. In here, there is some A contained in E with, you know that this measure of A. If you take a measure of A, this is less than delta. If this condition holds, definitely this integrable over E is also finite. Means it is in terms of epsilon. This is the theorem statement. Here we will prove in the two cases. In the first case, let F be a bounded and F is less than or equal to, bounded means there is some positive number M, it is F is less than or equal to M. Here we are choosing delta is equal to epsilon by M. Then for any set A is contained E because it is given with measure of A is less than delta, we have integral upon F over A is less than or equal to measure of A into it is bounded to M. Then definitely it is less than delta. Integral upon F is less than delta, that it can be written as M into MA is less than delta. Then M into delta become epsilon by M. Delta is equal to epsilon M is chosen here. Then epsilon the MM become cancelled, you get epsilon. Means the first part is F is bounded, means it is nothing to prove actually, but we can directly show that one. Suppose F is not bounded, then we can define a function. It is in terms of f and x. In terms of f and x, here we can choose f and x. It is in terms of f and x is f of x If f of x is less than or equal to n, and if otherwise we can choose as n, and x is in the measurable set and n running from 1 to etc. Here, Fn is a increasing sequence of non-negative bounded measurable function. If it is a bounded measurable function and also Fn is converges to f point wise, each point it is convergence. Then if it is bounded as well as convergence means we can apply to a bounded convergence theorem. Using bounded convergence theorem, there exists a integer n greater than 0 such that integral upon fn over e is greater than integral upon f minus, this can be written as integral upon over f over e minus epsilon by 2. We can usually, this can be written as integral upon f over e is less than integral upon fn over e plus epsilon by 2. But for arrangement, we can write directly, then integral upon e over f minus fn. We can rearrange this becomes epsilon by 2. There is a relationship between epsilon, delta, and n, and delta is less than epsilon by 2n. Then for every set A contained in E, because we have whatever the set we have chosen, it is inside the measurable set E with that measure is less than delta. That is the given thing. Using that concept, we have integral upon f over a can be written as adding and subtracting fn, means that is integral upon a f minus fn plus integral upon fn over a. It is less than, we can, as it is, we are written here, small n become capital N becomes small n, then plus n times, it is bounded n times measure of a, because it is a with respect to a. You know that measure of a is less than delta, less than epsilon by 2. Then 2n here, n will be there. Then this is less than, this is epsilon by 2 plus n times epsilon by 2n, n become cancel. Then epsilon by 2 plus epsilon by 2 is epsilon. Means therefore integral upon f over a is less than epsilon. Now we move on to one general Lebesgue integral. Let f be a non-negative, f be a measurable function on a measure set E. The positive part of f plus of f is defined as here f conjunction on O. Here for any x belongs to E, then f plus of x is equal to maximum of set of all f of x comma 0. Similarly, the negative part of f minus of f is defined as f minus f and conjunction of 0, then f minus of x is equal to maximum of minus f of x comma 0, or we can written as minus minimum of f of x comma 0. Combination of this we can write, f can be written as f plus minus f minus. Here for if f of x is greater than or equal to 0, f plus x is f of x and f minus x is 0. F of x is less than 0, f plus x is 0, and f minus x is minus f of x. If you take a modulus, then mod f is equal to mod f plus mod f minus. We observe that both f plus and f minus are non-negative measurable function. Here, I will give you a relation here. You know that f is a mapping. What is a mapping here? X to R plus. Or we can write R star here. Okay. It is a real valued function, extended real valued function. Here what we define, f plus of x is equal to f of x if f of x is greater than or equal to 0. Similarly, 0 if f of x is less than 0. Is it correct? Here, f plus is the maximum of f of x comma 0. Then you can see that here in this diagram, or I will write here. Here, this is a curve. Then here you can see that what is f plus? F plus part is here, you can see this one. You can see here, this is the part f plus. Again here, this is not considered because it is behind the line. Then this part, then this is the portion, we say that it is f plus. What is f plus? F plus is equal to maximum of f of x comma 0. Similarly, what is that here? In the negative part of the function, here, then here, then this lower portion will be there. Then we can make this into upper portion. Then again this portion. Means this will be comes to this side. Means here, this one, and here.